Going on, guys? In this video we are going to see how to calculate electric field caused by a ring of charge. Here we have a ring of charge. In order to calculate the electric field, what we are going to do is we are going to pick up a small segment. So let's call this is our small segment right here, and if we pick up this one, we are going to have small charge. Let's call that small charge dq, right? And also this distance is going to be small. This distance right here, let's call that distance ds, and the electric field is going to move away because this is a positive charge. So we are going to have electric field move away from this one. So let's call the electric field caused by the small charge is equal to dE and dE, and also we are going to have a small angle related to this. Let's call this small angle d phi. Okay, now we are going to create the equation. We are going to create the equation. If you remember electric field equation, that's is equal to kq over r square, right? So in this case we are going to use the same equation, but we are going to use the same equation for the small segment. So in this case we are going to have dE is equal to k dq over, this is our radius, r square. Okay, and this dq, this small charge right here, you can replace that one with lambda ds. Lambda is charge density, and if you multiply charge density with this small distance right here, that's going to give you the charge on that place. Okay, so we are going to do that here. We are going to replace this dq with lambda ds. So this is going to become k lambda ds, and in the denominator we have r square, and this is our r. And you can see if we pick up this one as this is r, and if you use Pythagorean theorem, r square is going to be equivalent to a square plus x square. Therefore r is going to be equivalent to square root of a square plus x square. So we can replace this r square with a square. Since we have r square, we can replace this one with a square plus x square. Okay, a square plus x square, and that's it. Now we have k lambda ds a square plus x square. This is for dE, but this one is going to have two components. Since this is not in exact x-axis or y-axis, this is going to have two components, dex and dey. But if you think about this components is going to be everywhere. Like if you take small segment, due to the small segment we have this one, but if you go along this circular charge, we are going to have ex and ey everywhere, right? And for example, if you pick up a charge right here, this ey will be in the opposite direction, right? So for all the y components will be on the opposite, like half of the circle will be in this side and bottom half of the circle will be in the other side. So the y components are going to cancel each other, so we don't have to worry about y because it's going to cancel. Okay, so only the x components are going to add up. We have to just calculate that value only. So here we are going to consider x axis alone, and if we put this one as dex, and dex is basically de cos theta, we can say de cos theta is equivalent to dex, de cos theta, and this is our theta. Okay, and then if this is theta, and this is also theta. If this is theta, this is also theta. So here we are going to put dex. That's going to be equivalent to k lambda ds cos theta and a square plus x square, and cos theta we know that that's adjacent over hypotenuse. Adjacent is a, so this is going to be multiplied by a right here and divided by the hypotenuse. Hypotenuse is r, but in this case r is equal to square root of a square plus x square, so we can write this one as square root of a square plus x square. Right, here we have power 1, here we have power half. If we add them together, like if we multiply them together, the power will add, that's going to become 3 by 2, right? So instead of writing like this, we can combine these two together and write a square plus x square power 3 by 2, and also we can multiply this a, Actually, if I write this one, I shouldn't write this cos theta. It's better to write in the next step because I replace this one with cos theta. Okay, I write this one in the next step. This is going to be k lambda ds over a square plus x square. Instead of cos theta, I'm replacing adjacent over hypotenuse. Adjacent is a and hypotenuse r. That's going to be square root of a square plus x square. And if we combine these two together, this is going to be a k lambda ds over a square plus x square power 3 by 2. Okay, so here we have this one. This is dex, but our purpose is to find E, the total electric field, right? This is for just a small segment. Now to find the total electric field, what we have to do is we have to integrate both sides. So if we integrate this one and in this side, that's going to give us the total electric field. Now let's go ahead and continue this one right here. And from this one, you can see if we integrate, that's going to give us E. And in the other side, we are integrating this one with respect to S, right? Surface. And for this circle, the surface is going to go from 0 to circumference of the circle. And the radius is known, that's x. And this is a circle, so 2 phi x is going to be the circumference for this circle, right? Since the radius is x, 2 phi x. And that's going to be the limits of integration. Here we are going to have limits of integration 0 to 2 phi x. But everything other than s is going to be constant because we are integrating this one with respect to s. Everything other than s is going to be a constant, so we can move everything to the front. So this is going to become, it's better to continue here because we need some big space. Let's continue this part. Okay, let's make this one bigger. Okay, let's continue this part right here. Okay, I'm going to continue here and let's get rid of this one. Okay, so here we are going to put E is going to be equivalent to this. I'm going to bring all the constants to the front, so this is going to be ak lambda divided by a square plus x square power 3 by 2, and then integration is going to go from 0 to 2 phi circumference, so this is going to be 2 phi x, and then here we are going to have ds. That's the only thing that is related to s. Other than that, we don't have any s right here. Okay, so this is the only thing, and if we integrate this one, this is going to become ak lambda over a square plus x square power 3 by 2, and this is going to be s, and that's going from 0 to 2 phi x. And if we plug 0, like if we plug 2 phi x, this is going to be just 2 phi x, and if you plug 0, the whole thing will become 0. So we only have to do the top part, and that's going to become ak lambda over a square plus x square power 3 by 2 multiplied by 2 phi x. And if you do the lower limits of integration substitution, that's going to become 0. The whole thing is going to become 0 because we are multiplying everything by 0. So that's going to be just 0. We don't have to worry about that part. Okay. Now let's continue this part right here. Let's get rid of this one. And let's copy these things down here. Also, we don't need this one. Okay. So let's continue here. Here we have ak lambda over a square plus x square power 3 by 2 times 2 phi x. So this is what we got. This is equal to E. Now what we can do is k. If you remember, k is equal to 1 over 4 phi epsilon naught, right? 1 over 4 phi epsilon naught. So we can replace this k with that one. So this is going to become a lambda times 2 phi x divided by 4 phi epsilon naught, and then a square plus x square power 3 by 2. From this one you can cancel this 4 phi and 2 phi. This is going to become just 2, and that's it, right? So this is going to give us a lambda x divided by 2 epsilon naught, 2 epsilon naught x square plus x a square power 3 by 2. And that's it. That's how we calculate the electric field of of ring of charge. Okay, so this is going to be the final solution. And for example, if you have smaller x compared to a, if you have a very long distance this a, we can neglect this x. So we can have another equation if you have a very long a, right? So in that those kind of situation, we are going to have E is equal to kq, capital Q, kq, small q, it doesn't matter, kqa, kqa x square plus a square power 3 by 2, and also this one can be written as kq over a square, because this is very small. So this is going to become just a cube divided by 2, and finally we will just end up with kq over a square. And this is like almost like standard form, right? But this is only possible when we have very large a distance compared to this x distance. Okay, so this is when we have very large a compared to x, very large, how we can say very large, like this. Okay, that's how we do this kind of problem. So I hope this helps. Thanks for watching.